Uh, Deja vu. I'm talking about, today I want to talk about query evaluation. In particular, we will start by reviewing some techniques for query evaluation in the static setting where the database is fixed. And we will see then how we can leverage some of those techniques in the dynamic setting where the database is changing and we want to maintain our query answer as the database evolves over time. Now, this talk will be a little bit heavy on the database theory side, where we will look at the complexity of different queries. And you might rightfully ask, why should a practitioner care about so much asymptotic complexity of queries? Let me give you an honest answer on behalf of the query optimizer team at Relational AI from our experience working in industry, and where exactly does complexity theory come into the picture. So first of all, from our collective experience, like at Relational AI, doing query optimization, having a query plan that has the right asymptotics is absolutely necessary, but it is not sufficient for good performance. In particular, if you end up having the wrong plan, let's say that runs in time n squared instead of n, there's no amount of engineering that you can do that can basically hide this. You can throw in all the GPUs, all the machines that you want. In fact, the more resources you throw at the wrong plan, the more trouble you will be getting yourself into. So of course, like having the correct asymptotic complexity of your query plan is the first single point of failure. It's not the only thing. There's still a ton of engineering to be done for good performance. Another lesson that we learned from our experience is that having guaranteed upper bounds really matter a lot. Like having, for example, a query optimizer that produces good or even optimal query plans 99% of the time is very good, like academically, it's like a huge success. But you would be surprised to know that in industry, such an optimizer would solve 0% of customer workloads. And why exactly is that? Because a single workload is like thousands of interconnected queries. It's enough to produce like a bad plan, let's say, that runs in the wrong complexity, and then the entire customer workload will just come to a complete standstill. And then you will end up getting a call over the weekend in the middle of the night, not to congratulate you on the 999 queries that run successfully, but on the very one that stopped the entire workload and is allocating thousands of terabytes as we speak, and so on. So this is basically the main lesson, is that actually bad scenarios do happen. We cannot just rely on heuristics. We really need to understand what is the worst case scenario that can happen, because it will happen eventually. The other thing is that, like, you will see some of the queries that we will be looking at today might be like too complex. You might ask, who would write such a query? And the answer is no human would, because most queries today are not really written by humans in the first place, or at least not directly. Instead, there are like higher level languages on top of database languages. And today, even people want to write their basically their questions in natural language, and they rely on many agents to produce the database queries. So by the time a database, like by the time the query hits the boundaries of the database system, it will be, in many cases, actually incredibly complex, following a pattern that no human would ever write, because no human ever wrote it in the first place. And with that motivation, I hope I made some case, again, based on not my own personal experience, but based on our collective experience in the query optimizer team at Relational AI, why we should care about asymptotics, even for practitioners, for asymptotic complexity. So I will start with some background about what we know about the complexity of query evaluation in the static setting. Then we will look at the dynamic setting. In the dynamic setting, there are two common scenarios, whether we have a stream of inserts only, or inserts and deletes. And then we will look at some future directions. So in the static setting, the problem that we will be looking at is the evaluation of a conjunctive query on a fixed database. For the purpose of this talk, I will be focusing the examples on full queries, where all the variables are free. But most of what we are going to talk about actually generalizes to many other classes of queries, including non-full queries, aggregate queries. But just to keep the examples focused, I will focus on full queries. So we have basically a join of a bunch of relations. Each one of them involves a set of attributes, x1 up to xk, and x is basically all the variables in the query. For example, which is an overly used example in database theory, the triangle query. We have 3 binary relations, and we are asking for triangles that are formed by these 3 relations. So what do we know about the complexity of this problem in terms of database theory? As it turns out, there are basically only 3 techniques that are basically responsible for the best complexity that we know for this problem for any query that we have looked at. And so we will take a look at these sequence of techniques. Each one of them will produce a better bound than the one before. The first technique actually is worst case optimal joins. And what exactly is so special about these join algorithms? They are multi-way. They don't join 2 relations at a time. They join a collection of tables at the same time. They are very suitable for graph workloads, whether it's like a knowledge graph analysis or analyzing social networks. They are very practical. They have been implemented in multiple commercial systems, including our system at Relational AI. At Relational AI, we rely on Julia's code generation in order to generate like a specific worst case optimal join code, machine code for a given query. So what do these algorithms look like? Luckily, they are actually very simple, which is a very strong point in support of these algorithms. So if you take the triangle query, a worst case optimal join is basically just a collection of nested for loops. Each loop is looping over the assignments of a given variable. So the first loop here is looping over the assignments of A from both R and T. The second loop is looping over the assignments of B, modulo the fixed A that we already know. And so on. The third loop is looping over C. It's pretty simple, just nested for loops. So why exactly is this all this fuzz about worst case optimal joins? What is so special about them? It turns out that they have this simple algorithm has very nice properties in terms of complexity. And in order to understand better their complexity, we need some context about the worst case output size of a given query. So we ask the question, if we have, let's say, this query, what is the maximum number of output size, or in this case, triangles that we can get? It turns out this problem has been solved a while back. There is a bound, a known bound called the AGM bound, which works as follows. If you take the product of the relation sizes raised to some powers, then this is an upper bound, a valid upper bound on the output size of the number of triangles, as long as these powers satisfy a certain property called the fractional edge cover property, which basically roughly says that every variable in the query needs to be covered by at least a total of 1. So for example, in this triangle query, if we pick these coefficients to be 1/2 everywhere, then the variable A is receiving 1/2 from here, 1/2 from here, it's totally covered. The variable B is receiving 1/2 from here, 1/2 from here. So this is a valid edge cover, and from there we infer that this is indeed a valid upper bound on the query size. So this is actually a guaranteed upper bound, which is actually quite important in practice. Like you can use this, for example, to decide how much memory you want to allocate, and you can never go wrong. This is not a heuristic. Interestingly, it turns out that this is actually a tight bound, in the sense that the best bound that you can infer this way is indeed a worst case bound. There's an actual database instance that can match the bound. And so what's all the excitement about worst case optimal joins? They run actually, their runtime is guaranteed always to be upper bounded by this bound. So the simple algorithm, the nested for loops that we were looking at earlier, runs in this runtime, which is into the 3/2. It's an interesting complexity. Where does the square root come from out of nowhere? But this is basically the power of information theory. So this is basically the first class of results that we have for static query evaluation. But it's not enough. Worst case optimal joins are not enough. We need a second technique, which is factorization. factorization is actually very useful and in fact unavoidable for long queries, which I will be giving you some intuition regarding what these queries look like in the practice. It is actually implemented at relational AI. And this is indeed like one of the worst offenders. If you don't factorize, you will indeed encounter queries that will run many orders of magnitude beyond what they should be running. In fact, there are many examples we see in the practice where if you fail to factorize, you will fail to terminate at all for certain queries. So what does factorization look like? Let me give you first like a slightly made up example where, let's say in this query, we have two triangles that join an edge BC. Now, this query, intuitively, you don't have to solve it in one bulk, because technically this is like two triangles. So you can solve it as a query plan where you have two subqueries. Each subquery by itself is just a triangle, and then you need to intersect over BC. And you can like use this idea to count the number of answers, let's say, to this query in time into the 3/2, because you just do it one triangle at a time. For every BC, you can count the number of these. Separately, you can count the number of A's, and just you multiply the two counts, which are computed separately. Instead, if you would try to answer this query as just one query, it would cost you time n squared. And from there, actually, you can extrapolate from this example. So here we just have two triangles. In general, we might have like an entire chain or even a tree of subqueries. Don't have to be triangles. They could even be just input relations. But if there is like a longer chain or a path, then if you do not factorize, you will never terminate. At relational AI, we have our own implementation of factorization. So first of all, we have our own language, which is a vast extension of data log. For this query, it will look exactly that you would expect like in data log. It will look like this in our language. This is basically the head. This is the body. And the way we implement factorization is as a logical rewrite that will rewrite this query into a sequence of subqueries in the same language. So we have a factorizer that will rewrite it into these two subqueries. The red subquery is for this triangle. And then we will use the result in the second triangle. Like you can think of the first subquery as we are already materializing for every BC the list of these. So that we are just left basically here with a triangle on this side. We already have a pre-filtered list of these for every BC. And for this example, after factorization, this will lower the complexity from n squared into the 3/2 plus output size. And interestingly, you can produce this into the 3/2 in a pre-processing phase. And afterwards, you can generate a continuing stream of output tuples without any lag, where there is a constant time spent between one tuple and the next, which is, in database theory, we call this property the constant delay enumeration. This is for this particular query. The general expression is basically to a parameter called the fraction attribute of the query plus output size. And this is basically the second fundamental technique that is used to lower the complexity of static evaluation. It is not enough. The third technique that is crucial is data partitioning. Now, this is actually not something fundamentally new to practitioners. Like even in like real, let's say, graph engines, it is not like it's not out of the ordinary, let's say, to isolate vertices in a graph with very high degree, let's say for in social networks. There are certain social personalities with way too many contacts, millions of contacts potentially. You don't want to process them in the same way you process like normal vertices. So it is typical.
It's a technical name. It's called the Justin Bieber effect. Because apparently this broke the several data mining engines back in the early 2000s. Because Justin Bieber, of course, for the older people here, Justin Bieber is very popular.
Thanks, Dan, for the background. So basically, there is an algorithm called the Panda algorithm, which basically explores the theoretical limits of this data partitioning approach. If we are allowed to do as much partitioning as we want, to lower the complexity as much as we can. This algorithm is exactly meant to do that. So it basically figures out a partitioning strategy that is guided by information theory, and then it picks a different query plan for each part. Like as a quick example, if you take a look at this 4-cycle query, it accepts at least 2 different query plans. You can either partition it vertically into these 2 parts or horizontally. No matter which query plan that you pick, you can always end up running in time n squared in the worst case. But if you partition your data carefully and use either one of the plan for each part, you can lower the complexity down to n to the 3/2 in this example. In general, for a general query, there is a parameter called the submodel width of the query. And for any query that have been looked at in the literature, so far, this is basically the best complexity that we know for any query that we looked at least as far as combinatorial algorithms go. Non-combinatorial algorithms are beyond the scope of this talk. So like for the purpose of this talk, we will treat this as basically like the best complexity that we know of for any query. Just to give you a very quick brief overview of how Panda works. Panda always like analyzes the query using information theory, but at the very end, regardless of what it does, it will just produce for you a query plan that uses 3 kinds of operations. There is a partitioning based on degrees, so we can partition, let's say, the relation S based on the vertices B, whether they are like Justin Pieper grade, in which case we put them in the VIP section SH, or they are just regular vertices, we put them in the light section. There is a join operation. Usually we perform join only over light vertices, and instead we perform projections on heavy vertices. And these are basically the only kind of operations: partition, join, projection. These 3 operations at all, at least from theory perspective, they are sufficient to produce the best asymptotic complexity for any query that has been studied in the literature. Now, of course, in practice, there are more techniques. So far, I only mentioned the 3 techniques. I'm claiming that they achieve the best complexity. In practice, there are a lot more. There is like a parallelization. There are hash joins. These operators don't really like lower the complexity, at least not in the RAM model. They, of course, can help you in practice a lot, lowering the runtime like by the huge factors sometimes. But for the purpose of this talk, we are focusing on the asymptotic complexity, and these 3 techniques are sufficient. And with that, now our next target, yes.
So for the does duration add on any data partitioning like in your query engine, or is this too impractical for query engine?
We haven't. Okay, good question. We haven't actually implemented like Panda, and no one has implemented Panda in production because like the algorithm is a little bit of an overkill in the sense that it over partitions. However, so we at Relational AI, we haven't yet implemented any form of partitioning that I'm aware of. But other engines have potentially, at least some of them have some limited form of partitioning, at least at the level of just isolating heavy hitters and treating them separately.
But I don't know, it's done for parallel query processing. When you have partition, then you do want to set aside the heavy hitters.
So now we want to basically take a look at dynamic query evaluation and how much we can leverage our experience over there. So what is the problem of dynamic query evaluation? We have a query just like before. We will assume for now that the input relations are initially empty. We can relax this restriction, but for now, let's say that they are initially empty. And now we are receiving a stream of inserts and deletes into these relations, either insert of a tuple or a delete of a tuple into these relations. Now, what do we want to do? After each one of those inserts and deletes, we are allowed to spend some time processing this insert and delete. This time it's called the update time. After the update time, we are required basically to produce a stream of inserts and deletes into the output. So every insert into one of those relations could potentially trigger many inserts into the output, and vice versa. Every delete might trigger many deletes into the output. So we are required to produce a stream And it should be like a no lag stream where there's like just constant time between every tuple and the next. And the challenge here is to minimize this update time, which could be amortized. We could be, it's also good enough to, in some cases, to consider the averaged update time over multiple updates. So let me give you an example. If you consider the triangle query again, now initially those relations are empty. And now let's say we are receiving a stream of inserts into the input. I'm denoting an insert with a plus. So we are inserting a single tuple into R. But the output is still empty because there is nothing in S and T. Now we insert another tuple into S. The output is still empty. We insert another tuple into T so that these three tuples, the red, green, blue, they make up a triangle. And now in our output stream, we must emit a new triangle as an insertion into the output stream.
To help me understand what's the typical application of these dynamic queries.
Re-evaluation after the input changes, which is like very common in practice, because in practice tables keep changing all the time and we have views on top of them. So we want to basically just change the answer without recomputing from scratch. Because usually like the size of the change is much smaller than the full size of the database. There is usually like a few more vertices that need to be added to an existing social network. You don't want to rerun your entire analysis of the social network.
What I should mention for monitoring queries, so you want to monitor the health of your data center, and the logs are continuously being updated, usually just inserts. But you want to have all these counts and all the aggregates, you want to have them up to date. That would be.
Oh, sure. Is this also known as incremental evaluation, or is that just
what is that?
Is dynamic query evaluation the same thing as incremental?
Yes, yes. I think maybe the term dynamic algorithms is more popular in the algorithms community. In the database literature, is probably the IBM is more popular. But yes, in our context, they are the same thing.
So it sounds like incremental maintenance problem.
Yes. Yeah, I should probably for the future, I should probably advertise it like this. Yeah, and then in this example, let's say if we have another insert, that does not change the output. Notice that we are not really reporting anything here. The output did not change. We are only reporting the change in the output, not the output itself. So here the output remains the same, so we don't report anything. Now let's say if we delete the green tuple, now this output tuple must disappear. So now we have to report a delete in the output, and so on. So basically, we have a stream of inserts, deletes into the input relations. We are producing a stream of inserts, deletes into the output. And this is actually quite useful because like you can chain the output of this query, you can use it as an input to another query, and you have like streams propagating all the way from inputs to the outputs until across multiple views. And there are two typical settings. There is a setting where we only have inserts, we are only adding facts, and then there is a setting where we have both inserts and deletes. We will start with the inserts setting because it's simpler. So basically, in the static setting, we saw that we could achieve basically three progressively like improving bounds. There's the AGM bound, we improved over it, and then we improved over it again by first factorization and then Panda. So now what is the question, or at least a first question to ask when we move to the insert setting? The first question at least that we ask is, if we have a stream of n inserts, can we process all these inserts in the same time as if we were doing a static evaluation of a database of size n? Like in the static setting, you can think of it this way. In the static setting, we already have all these inserts, and we are only required to produce the final output of the query. In the insert setting, we don't see the future. We are only seeing one insert at a time, and we are not allowed to wait until the future. After every single insert, we have to report the immediate output tuples that were resulted from this insert. So this is actually like a strictly harder problem, but we are still aiming or hoping at least to achieve the exact same bound. So for example, instead of the AGM bound, if we want to process n updates in combined time, which is the AGM bound, it basically means that the average time for every insert is the AGM bound divided by n. So this will be like our first target. From there, we will probably see whether.
So sorry, another question.
Are we so in this streaming system, are we assuming like sliding window where like there's no sliding window, just keep increasing the number of tuples?
There is no sliding window. Like you can mimic sliding window manually if you start deleting tuples that fall out beyond, beyond like a certain threshold in the past. So you can manually simulate a sliding window, but the model by itself does not come with a sliding window. Yeah, and similarly, instead of aiming for this bound in the static setting, we want to aim for this averaged time in the insert setting and so on. And now we want to revisit each one of those questions. Starting with the first question, like one way to interpret the first question is, does there exist a dynamic version or an incrementally maintained version of a worst-case optimal join that maintains the exact same runtime guarantee, except that it does not see the future, it's just receiving one tuple at a time and reporting the output one tuple at a time? It turns out that the answer is luckily yes. And it's not even that complicated, which is, again, it's actually the simplicity of worst-case optimal joins is actually a huge plus sign for them, especially for practitioners, by the way. So why is this interesting? So let me tell you what do we gain from this, let's say in this example, in the triangle example. In the triangle example, the AGM bound is into the 3/2. It is not hard to create a scenario where inserting a single tuple will force us to do a linear amount of work, an amount of work ON. But if this result basically tells us that the average insert time is always square root of n, it can never exceed square root of n. So we have basically a hard guarantee that even if one insert takes time n, this can only happen if it is averaged out by previous inserts that were very cheap. And this is like an actual guarantee. This is not a heuristic. You have an provable upper bound. So how do we prove such a result? Suppose that we fix the values of a and b into some constants, little a and little b. So this query, we call it, let's say, a residual query. It only has c as a variable. It's a much smaller query. It turns out that the AGM bound accepts a very nice property, which is the sum of the AGM bound of this query is the sum of the AGM bounds of this query over all possible values of these constants a and b. And why is this useful for incremental maintenance, at least under insertions, is that every time we insert a tuple into R, a new tuple, let's say R little a, little b, in order to report the change in the output, we have to solve the residual query for this particular AB. And now we have the guarantee that all these residual queries that we have to solve for every single insert, all of them are bounded by the static AGM bound of the query. So it turns out worst-case optimal joins were made to be incrementally maintained, at least under inserts. So like the maintenance algorithm is what you would expect, except that you would be, maybe the only difference is that you would have to maintain two indices for every relation. So for RAB, we also need an index in the reverse direction, BA, and you will see in a minute why. So every time there is an insert, you will need to insert in both indices and solve the residual query. If there is an insert into, let's say, S, you will also need to insert into the other index, but now you will have to solve the residual query. But here we will need basically to access the A values in R for the given B. And this is why we need the other index.
So Mahmoud, this means that in practice, the time will double because you need to do insertions in both indices. The time for guaranteeing incremental maintenance for guaranteeing dynamic query processing will be double of the time that you would get if you are allowed to compute the query only once statically.
Yes, it's double, not square, not in the exponent. But yes, that's true.
Yeah, but you're losing on the leaderboard, right? You're no longer the top tier.
I mean, there is no free lunch. Ultimately, you would have to expect that there will be a loss somewhere. And we do have, like at Relational AI, we do have our implementation of incremental view maintenance. It's actually more complicated than what I'm about to show you. I'm going to show you an oversimplification because in our case, we don't handle inserts separately from inserts deletes. So like our full maintenance mechanism is count-based because it has to support deletes. But for now, I will oversimplify it a bit. So in our case, like this query is written like this in our language. In order to incrementally maintain it, we also apply a logical rewrite. We rewrite it into a collection of delta queries. Each one of those delta queries will basically compute the change in the output with respect to some of the input relation, to one input relation or more. And it will also perform some re-indexing depending on the need, because we also need to re-index. And then we will collect all these deltas in the output in a frame rule. And this by itself will achieve the same guarantee. So just because we are evaluating like every one of these rules using operational joins, this logical rewrite is sufficient basically to get a dynamic version of operational joins. So think of it this way, like these two concerns can be separated. The concern of our static vertical joins and the dynamic aspect, they can be like totally separated. We just need to worry about a static evaluation for every rule using operational joins, and a logical rewrite to maintain. And you get basically for free, or almost for free, a dynamic vertical join. So this is how you can get a dynamic vertical join. Now, what about factorization? Can we really get, basically create a dynamic version of factorization? Turns out the answer is also yes. And let me give you an example. If we revisit the same two triangles example from before, we will basically do the same thing. We will create basically a query plan where there is a query for every bag. The only difference is that every one of those two queries will be maintained using the same dynamic vertical join algorithm that we were just looking at. So this is basically just a triangle query. We know that we can maintain it from before in the same runtime as a static evaluation, and the same applies for this. And now, if we have, let's say, an insert of a new tuple into R, how can we enumerate the answers? We can enumerate the C values using basically the green bag. And for every C value, we can enumerate the D values from the red bag. And this is sort of like a lag-free enumeration. In this enumeration, we will never there will never be any trial and error. We are always guaranteed that every step we are producing an output tuple. Now, this is the theory. In practice, how can you implement this, or how did we actually implement this, at least at relational AI? There is also a separation of concerns here, because this query, we receive it like this in the static setting. We have a logical rewrite, which we have seen before. This is just not yet concerned with incremental maintenance. We rewrite in two subqueries. This is for the static setting. And then there is another logical rewrite for incremental view maintenance, which will rewrite each query into a series of delta queries. And now, just like before, there is like a separation of concerns. You can perform factorization as a logical rewrite, incremental view maintenance as another logical rewrite, and you will still maintain the exact same guarantee of a dynamic version of a factorization just by applying incremental view maintenance at the end as an extra step. And this is how we can get a dynamic version of factorization. What about Panda, the data partitioning approach? It turns out that the answer is still yes. And just this is actually an ongoing work with the database group at University of Zurich. Just to give you a very brief idea regarding how we can prove something like this. Remember that Panda fundamentally has only three kinds of operations. There is joins, there is projections, and then there is partitioning. Now, joins are easy to incrementalize in the sense that if we have a streams of inserts into R and S, you can easily turn them into a stream of inserts into the head. Projections are also easy. If you have a stream of inserts into the original relation, you can turn into a stream of inserts with the projection within the same time. This partitioning step is a bit hairier, because if you have a stream of inserts, a value B might become heavy at some point in time. Like the first time we encounter Justin Bieber, we don't know how famous he is. We keep getting more and more connections. At some point in time, oh, we find out that he's a big deal. And then we have to move him from Ps into VIPs. And then, but then in this movement of data is actually a problem in the insert setting, because we are not really allowed to delete and reinsert. But it turns out that there is a solution to this problem. I'm not gonna talk about it right now. I'm gonna leave this as a brain teaser maybe for the done. So apparently there is actually a dynamic version of Panda, which we like to call Kung Fu Panda. It's a still work in progress. So it turns out that life is good in the inserts world. And now we get greedy and start asking about the inserts deletes world. In particular, we just want to see how we can potentially mimic the exact same results, but under the insert delete setting. Starting with the AGM bound, can we really achieve the same bound in the insert delete setting? And it turns out that the answer is a resounding no. And this actually excludes also the other two bounds because they are even better than the AGM bound. If we cannot achieve this, we cannot achieve those. So how do we know that? It turns out that if we take this very simple query, this simple query has an AGM bound of n. You can solve it in linear time. So basically, if we were going to achieve this, we have to achieve an update time, a constant update time, a constant amortized update time. But as it turns out, if we ever manage to go beyond like a square root of n update time, then there is a well-accepted complexity conjecture that would fail. This conjecture is called the online matrix vector multiplication conjecture. And like very roughly, it's basically about the complexity of multiplying matrices in the incremental setting where we are receiving a stream of vectors rather than the matrices in full. So basically, like long story short, we cannot really afford for this conjecture to fail. Otherwise, the complexity police would come after us. So this basically means that we are not really allowed to go below this update time, which basically means that we cannot achieve this bound. But then this begs the question: what was so hard about this query? Like, if I give you an arbitrary query, how can we decide what is the target? What is like the best, or at least a lower bound on the best update time that we can hope for? Can we really develop like a meaningful lower bound for any query that explains the hardness of this query?
So Mahmoud, can you give us a quick intuition? Why is this? What exactly makes it difficult to maintain this query under inserts and deletes? It must be a delete operation. Which delete operation is difficult to maintain? Maybe deleting from S, or no? Deleting from S should be easy, no? Deleting from R may be difficult.
I actually will come back to this particular query in maybe 4 slides to show how we can explain the difficulty of this query without relying on external conjectures, like a database centered or in this case self-centered explanation.
Okay, sounds good. Thanks.
Okay. So now our problem was we have this query and we want to maintain it under a stream of, we have a stream of inserts and we want to produce a stream of deletes. And we want to basically figure out a lower bound, or at least what is the best we can ever hope for on the update time for this query. In order to develop a lower bound, we need an easier problem. We need to create an easier version of this problem. And then we can ask what is the lower bound or the best we can do for that easier problem. It must also apply for our original problem, the harder problem. So what is the easier problem that we are going to choose here? In this problem, in our original problem, we don't really see the future. We are just receiving one tuple at a time, and we are required to produce the output at that point, or the change in output at that time. In order to create an easier problem, we will allow seeing the future. We will provide the entire stream upfront, and now we just want to produce basically the output. So, for example, in this easier version of the problem, we are upfront given this extended relation R bar, which has all the tuples where every tuple has its lifespan. So we are already told upfront that there is a tuple A1, B1 that will be inserted at time 1 and deleted at time 8. And same thing, we are already given upfront a relation S bar. We are told that B1, C1 will be inserted at time 2 and deleted at time 5, and so on. And now our target is to evaluate a query that looks like this. We are looking for like triangles ABC, where these 3 lifespans, the lifespans of the 3 tuples overlap, and we want to report their intersection as the lifespan of the tuple in the output. So in this particular case, if you solve this query under this semantics, you will get that there is a triangle A1, B1, C1, whose lifespan is from 3 to 5, which is exactly this. Now, this problem is easier than this because here we can see the future, here we cannot. And the two problems are connected in terms of the output size. So here you can always show that the output size or the length of the stream is twice the number of tuples that we have here because every tuple will be iterated twice. In particular, we can reduce, so this problem is a static evaluation. There is no incremental maintenance here because we already know everything up front. And we just want to evaluate this, let's say, in some time into the power of C. But because this is the easier problem, this reduces to the harder problem, which is the incremental maintenance of this, with average update time into C to the power of -1, which is the same thing as saying all updates in time to the power of C. So this easier problem reduces to this problem. And this is actually, so this arrow here represents a reduction. Now, lower bounds in complexity theory move in the same direction as your reduction. On the other hand, upper bounds move in the opposite direction. And this actually can be very confusing. And yeah, so you should always make sure that you are basically like using your, or when you try to prove a reduction to get some lower bound, always make sure that you have the direction of the reduction correct before spending months trying to do it. In fact, there are PhD dissertations out there proving reductions, unfortunately, in the wrong direction, which is, it's actually for real. So now the nice thing is that now we can use lower bounds on this problem to get lower bounds on our original problem, the insert delete. But now with this, ask the question like what kind of lower bounds do we have on this problem? And in order to understand that in this particular case, we will start by trying to solve this problem, which luckily for us, it turns out that we already know how to solve this problem, the static evaluation of queries that look like this. I'm not going to go into detail because I don't have that much time left. So remember here, roughly our problem is to compute this join where we also want to detect intersections of the lifespans of these tuples so that we can report the intersection. Very briefly, in order to do this, we will basically use a segment tree over the time dimension. A segment tree looks like this. It's like a tree where we are dividing like the range in half and then dividing recursively every half in half and so on. And now we will basically like detect intersections over this segment tree. So basically, we will break each one of those lifespans into a collection of lifespans over this segment tree. The nice thing about segment trees is that you can basically reduce your operations from detecting intersections into detecting strings that are a prefix of one another. So instead of looking for intervals that intersect, the problem becomes in this view, looking for strings that are basically a prefix of one another. And this actually basically ends up reducing, solving this problem into solving a bunch of queries that look like this. In each one of those queries, we are looking basically for an interval from, so for example, if we take the first query, this is asking for intervals from R that contain some interval from S that contain some interval from T. There are actually 3 permutations in total, so this is why we have 6 queries. In the dyadic world, like briefly, 2 intervals can intersect if and only if one of them is a superset of the other. You cannot really have partial overlaps. So basically, for this problem, we know that we can basically reduce it to solving these, for this particular query, we know that we can reduce it to solving this 6 distinct queries. Each one of them is detecting basically like a different combination. This one is detecting intervals where R contains S, contains T, and so on. And so basically using these this segment tree view, we can reduce the first problem to the second. And the output size roughly remains the same. And the nice thing is that these queries are just conjunctive queries. We know exactly their worst case output size bound. It's basically the AGM bound. Interestingly, in this case, it turns out that this problem also can be reduced to this problem. So this is actually one of the luckiest kind of reductions because both of these problems can be reduced to the other. Therefore, you do not have to remember which lower bound reduces to which and which upper bound reduces to which. It's the least confusing kind of reduction. So now let's go back to the picture and see what do we know about the problems we have studied so far. We talked about incremental maintenance of this query, the triangle query. And then the easier problem was basically the static evaluation of this query, which has intervals. And then there's the evaluation of these kinds of queries, Q hat. This problem, the easier problem, is reducible to this, and these two problems are equivalent. And then again, remember, lower bounds move in the same direction as the reductions, upper bounds move in the opposite direction. Now, what is the best upper bound that we know for this query? It's actually the submodular width, the bound that is achieved by the Panda algorithm that we saw earlier for static evaluation, at least as far as combinatorial algorithms go. Therefore, we cannot basically exceed this update time for this query unless we basically discover something for static evaluation that improves over the Panda algorithm, that improves over the state of the art in static evaluation. Now, this is sort of like a neat observation in the sense that we are linking the fates of dynamic evaluation to static evaluation. In particular, like here's one way to think of it. There is no point in trying to push for an update time that is lower than this bound, because you might as well go to static evaluation and try to invent a static evaluation algorithm that is better than Panda. This is like one way to interpret this. Now, back to Dan's question, why this query is hard? Or at least how can we explain this without the OMV conjecture? One way to explain it is that when we apply this reduction, one of the queries that we will get is actually contains a triangle, which basically means the following. It basically means that we cannot solve this, we cannot maintain this query in update time less than square root of n unless we evaluate the triangle itself in time less than n to the 3/2, which is possible, but not through combinatorial algorithms. So this now basically like links the hardness of maintaining this query to the static evaluation of the triangle query. Now from there, so this doesn't explicitly answer your question, Dan, which is what is a worst case scenario for this query that shows that you cannot exceed this better? In order to construct a worst case scenario, you can start by constructing a worst case scenario for the AGM bound of this query, and then translate it back where you interpret these z variables as time and translate it back into inserts, deletes. I haven't done this, but we can work it out maybe later. So this is also the cute thing about this reduction, is that you can use it to extract worst case scenarios for inserts, deletes, using the worst case instances for static evaluation. Okay, I'm almost out of time, but I'm almost out of content anyhow. So far in the insert only setting, we saw upper bounds, we saw algorithms. For the insert delete setting, we don't yet have we haven't talked about upper bounds, we only talk about lower bounds. For acyclic queries, including all k-path queries, all of them can be maintained using the upper bounds or the techniques that we already discussed. All of them can be maintained in constant amortized update times. On the other hand, the lower bound that we just saw implies like different lower bounds on like acyclic queries. As you can see, as k increases in a k-path, there is a lower bound that actually keeps increasing. And for cyclic queries, like there's basically a similar phenomenon. For maintaining, for example, k-cycle, we have certain upper bounds inherited from the static evaluation in submodular width time. We have lower bounds which are actually higher, and the gap can also keep growing. In some sense, this actually shows or proves that there is actually a gap between those two settings. Insert delete is inherently more difficult than insert only, and now we basically have a way to quantify that for different queries. Now, some of those upper bounds have been achieved by different algorithms that are made for certain queries. So this upper bound is achieved. These two have been achieved by the IVM epsilon. This upper bound not only has been achieved, but has been broken by a small epsilon. But how could a lower bound be broken? It has been broken because the algorithm these folks use is non-combinatorial, and the lower bound only applies to combinatorial algorithm. So in some sense, they cheated their way around the lower bound.
Yeah, by this, you mean that they use sparse matrix multiplication?
Surprisingly, yes. And the reason I'm saying surprisingly is that if you think about it, the online matrix vector multiplication conjecture, one way to interpret it is the following. So we know if you have two matrices, you can multiply them faster than n cubed. But the online matrix vector multiplication conjecture basically says, if you are receiving one of the two matrices as a stream of vectors, then you cannot do better than n cubed. There is no Strassen. So this is why I was actually surprised by this result, that they did actually find a way to utilize fast multiplication in the incremental setting. Let me wrap up. So what do we know so far about upper bounds for insert deletes? So these are, all these upper bounds are made are achieved by algorithms that are designed to specific queries. We don't yet have a general framework that can achieve an upper bound for any query. So where do we stand on the upper bounds front? First of all, instead of using a Q, we should be using a Q hat. This is basically what the lower bound justifies. So now we have to revisit all the questions, all the bounds that we discussed before, but we replace a Q with a Q hat. And we start with the AGM bound. Can we achieve this bound? The answer is yes. And even better, it turns out this is worst case optimal with respect to the length of the output stream. And this is actually not hard to prove because eventually we reduce the maintenance of a Q with a static evaluation of Q hat. So we can use basically the AGM bound of Q hat to construct worst case instances. But still, this bound is not very interesting. It does not achieve any of the cool lower bounds that I showed you on the previous slides. Can we achieve now, can we do the same thing for factorization? It's still open. We made a claim about this in the recent POTS paper, but there is still a gap in the proof that we are trying to, that was detected, and we are trying to close it. And by extension, it's still open whether we can achieve the sum order width. We are working on this by the we here, I am also including the database group at University of Zurich. So where do we go from here? Like the first two obvious questions is basically achieving those two bounds that are left open. The other direction is how do we go from amortized update time to worst case update times? We know for a fact that some of the update times will necessarily have to increase if you require them to become worst case. In fact, even in the triangle case, we know that the update time in worst case will be higher than the update time in the amortized update time, but we don't yet have a clean characterization of what is the worst case update.
Mahmoud, what do you mean by this? By worst case replacing amortized time? What should change?
Yeah, so for example, in the triangle case, right now, we say that there is an upper bound of square root of n on the update. We can indeed create, actually, it's not hard to create a scenario where a single update will force us to perform a linear amount of time. But we have a proof that this cannot happen very often, in some sense. If this happens, it must have been the case that there's like a linear number of updates that were very cheap.
Do you want every single update to have
let's say square root of n, but we know, for example, that for the triangle, I don't think this is possible. I will have to double check. But for some of those queries, we know that you cannot really close this gap, but we don't really have a clean characterization.
Thank you.
And then the other, yes.
The existence of skewed entity, if there's such an entity, you almost certainly couldn't do.
Yes, yes,
Right.
yeah. Now there is still a hope to improve the complexity, because even if there is a skewed entity, like in our case, we just allow like the update time is only measured from the beginning of processing the update to the time where we start like emitting the output as a stream. So you can still hide behind the output size, but you need to be able to be ready by then to start emitting the output as a stream. And this is exactly why I mentioned that here, like this AGM bound is versus optimal with respect to the length of the output stream, in the sense that if you are not allowed, or if you are allowed to hide by the length of to hide behind the length of the output stream, then this is indeed the best we can do. But we know that, like in practice, there are results that assume that okay, we can just delay the output or just start emitting the output. In which case, we can do better. Now, the last basically direction, which is the most futuristic, is can we really utilize fast matrix multiplication in general for these incremental maintenance. And this is actually, of course, like just on the theory side. On the practical side, there are many more questions for incremental view maintenance. I haven't collected an explicit list, at least for this talk. One of them is even just the computational model. What is the right computational model that captures that mimics it closer, like the computational scenarios that we have in practice. That's all I have for today's story. I run a bit over time.
Perfect. Thank you. Okay, so now we stop the recording and we open the